do this each time, okay? So I will try to pre-record the lecture. So I will put all the theory there. So I'm going through slides there with explanation. And on our live sessions, I'm going to be more, to dedicate them more to sort of nice parts like practical application and maybe some points here and there. I would like to explain certain moments in the theory. So it's going to be more loose. It's going to be more informal. But today's lecture is going to be kind of more formal. I'm going through the material. Maybe not. I'm not going to tell all these, very detailed fashion through all the slides, because I have already pre-recorded version. By the way, I will show you this. Let me. Okay, well, it's not this one. What is this one? Okay, this is. So you see the page of Canvas page of this course. So and then you click on modules, and then there is this first module, analysis of variance. So we'll do 3 lectures on this. It's actually kind of with respect to theory, this most difficult one, but on the exam, on the other hand, in the exam, people have at least problems with this topic, because exam questions are kind of not so difficult, but the theory for this topic is in principle very difficult. So this is my lecture, which I recorded yesterday for this lecture, for this first lecture. So we're going to make acquaintance with ANOVA today. And then the next lecture we will continue with ANOVA, but two-way ANOVA. And then in the last lecture we will treat ANCOVA, LASSO, and multiple testing. So LASSO I already treated previous year, and I included one more topic, multiple testing, this year, in a very light form. Don't worry. So these are kind of light subjects. And they're kind of interesting, and they're very popular in practice, and they're simply nice. Okay, so then when we are done with this, and then will be nonlinear regression and generalized linear models. You're not seeing this in time series, and then there will be course overview, and then there will be I will put a practice exam online in due time, and I also put last year exam with solutions to practice. Okay, so there will be enough for you to practice for exam. According to as to exam, it's not clear yet. If it's online, then I will have to think another form of the examination. It maybe be more like open book exam. So therefore, I will have to rethink the structure of the exam. So it used to be just usual standard exam, right? Without open book, so you had to sort of it was classical form of the examination. But if it's online, then it should be I will have to think and redesign the examination. It's not clear yet. It's the status of the exam is not confirmed for some reason. Okay, that's it. What else? Other questions? So please go ahead and put them in the chat. So let me stop sharing here. Okay. So let us then go through the lecture. So let me start sharing a lecture. Here it is. Okay. So we start with the first topic, analysis of variance. So again, I'm going to be sort of not as thorough as I usually am when in the live lectures, because I already made a pre-recorded version of it. Because otherwise, if I do that again, it will be just double work for you and for me. So there is no point. So again, let me emphasize this. I will make a pre-recorded lectures. They will be slightly shorter than, they will be around 1 hour, maybe a little bit more than that. And we'll concentrate all the theory thing there. And here it will be just sort of on top of that, going into some points. And maybe I will do some explanation. I will do some R demonstration as well today. I hope I will do that too. I will show you how to apply R commands for to do the analysis of variance, some tricks, and maybe a little bit of theory, reminders about some mathematical facts, and so on and so on. Okay, that will be the contents of our live sessions. But today a little bit more theory as well, because it's the first time. Okay, so analysis of variance. Well, here's the topics for this lecture. Basically, it's just we are going to introduce one-way ANOVA. That's it today. It's just and then some model diagnostics. Actually, model diagnostics is very important because this is something you always have to do in your assignments. Oh, about assignments, let me say that I actually have some sort of template. Okay, it's also available on Canvas. It's a Markdown file which you can use as a template for your assignments. It's very handy. You don't have to. It's not obligatory, but it's kind of a handy thing. You just put your text and your R commands in this Markdown file. And then you make a PDF out of it, and so R takes care of all the graphs and all that, and actually you can put LaTeX in there, so also theoretical part can be done there. You have to install RStudio, of course, in the right way, so that everything is in there. So you install first R, well, but you should know that, and then on top of that you install RStudio, and then you can do Markdown things, okay? And then just have a look at the template file, and you could use it as a, well, maybe I will show it in the second half, how it looks like, okay? What is RMD file, which is a Markdown, which produces PDF, and that would be a nice looking report. Okay, but let's just start with the theory. So here's the six points of today's lecture. Okay, we start with an example. Just two coffee distributors in two locations in Amsterdam and Rotterdam, and we just collect the data which consists of sales. Okay. And then the question is, are they different or not? Does it matter whether you are selling coffee in Amsterdam or in Rotterdam? Okay, that's basically the question. Okay, that's a very classical thing. That's just t-test, okay? T-test for unpaired samples. So because two samples are unpaired, and then they even may have different number of observations. So basically, let me just not be too let me not dwell on this too much. It's just t-test hypothesis. We have two normal samples with possibly different means, and we would like to test whether means are the same or not. And then we assume that everything is normal and they have the same variance. Okay, and then we sort of construct t statistics. Okay. So that's based on pooled sample standard deviation, which is here. So this is the formula for this. At the end of the day, we just need to compute the statistics, okay? And that statistics has t-distribution, okay, according to theory, with how many degrees of freedom, okay? So NA plus NB, so this is 10 outlets and 10 outlets in Amsterdam and 10 outlets in Rotterdam. Why is it B and B? It has to be in R, okay? Number of outlets in Rotterdam, I will correct that. So it's t-distribution with 18 degrees of freedom. And then we have to, of course, the next step, we simply compare it to the quantile, okay? And then if we are just, if this number is very big, okay, big enough so it goes over that quantile, then we reject H0, okay? And then in this particular case, the value of our statistics t is equal to minus 2.55, and then quantile is 2.1. So it is bigger than quantile, so we reject H0. Or alternatively, that's always the alternative, we can do testing through p-values. We simply compute the p-value. So now you should understand that this t is random variable according to t distribution with 18 degrees of freedom. And this t small is nothing else but that's just exactly the value of the observed value of that statistics, okay? So you shouldn't confuse this big T here with this big T here. This big T here is a random variable which has that distribution, and this small t is exactly the value which this statistics takes, okay? You compute that and it's a realized value, so it becomes a number. Okay, that number you substitute here, you compute this probability, and that probability turns out to be 0.019, so it's 0.2 approximately, and this is less than 0.05, so p-value is very small, well, smaller than 5%, and therefore you reject H0. That's just an equivalent way of doing the same thing which we did before here by quantile, by comparing to quantile. Okay, so that's it. So that's easy, right? We did this, and you probably did this in your statistics course. This is the classical stuff. It's a very, of course, important test. In fact, if you have two samples, if they are normal, that's the best you can do. You cannot do better than that. If your problem is a testing problem, that's actually the best you can do, and one can prove that. But imagine now that there are 5 locations. Now we have 5 cities. I don't know, how should I put that away? So, okay. I don't see my slides. I don't see because of the Zoom. So 5 cities: Amsterdam, Den Haag, Haarlem, Rotterdam, and Utrecht. And of course, sales are all different there. But the question is, are they significantly different? Okay. Then we can formalize the question as follows. So they're all coming from normal distributions, the same sigma, for instance. Okay, let it be the same thing as before. But, and the problem is now that all of them are the same. Oh, sorry, H0, the zero hypothesis is that mu1 is equal to mu2 and so on is equal to mu5. That we want to test against that at least there are 2 for which they're not the same. Okay, so t-test is not going to work because it works only for 2. That's it. So that's its scope. It cannot go any further. So, and then just to somehow to approach this problem, Fisher, that's the guy who's considered to be a founder of statistics, he played a very prominent role in actually establishing statistics as a discipline. So he's considered to be a founder of statistics by many, but many are not happy about this guy. So it's a bit controversial, but his role is, of course, very acknowledged by all the people in certain aspects. And he actually developed analysis of variance. It's due to him totally. So he was the one to invent that, and then it is still used widely, and it's a very, very popular technique, and we are studying it. So what else? What do we want to know? So since we are still studying it, so it's a really important and a useful technique in practice. Okay, so we just simply extend basically t-test. That's the idea. Okay, let's just fix some terminology for one-way ANOVA. So this total sales is going to be a response variable, and then this location, which is a city now, is going to be called a factor or effect. Okay, so response variable is always is looked at as is treated as a continuous variable, although it's not in this case. You know, total sales these are just euros and cents. Okay, so it's a discrete thing, but you could think of that as being continuous. in this particular case. And factor is always discrete, okay? So it has number, it has some different values which are called levels. And it doesn't matter how we call them, what they are. Could be numbers, 0, 1, 2, could be names, or could be, I don't know, colors. It doesn't matter as long as they're different, that's it. And therefore they're called categorical variables. And there might be an order in those levels, but it's not really important for the analysis. Okay, here's some examples, and let's just name the ones. Systolic blood pressure, for instance, that would be response variable, and then possible factors, smoker status, for instance. Smoker or not, okay? Yes or no, or smoker or not, or 0, 1. Whatever way you encode that, doesn't matter. And then, for instance, marital status, yes or no, and all the other things. But for instance, variables like age, weight, or height are not in principle factors because they're continuous, although you can make them factors, right, if you split in groups. But in principle, they're not factors, but they can be included in analysis. And then we are talking about something which, when we include factors and continuous variables, and that's exactly what we're going to treat in the last lecture, in the third lecture. Then we are not in the setting of ANOVA, we are in the setting of ANCOVA. Okay, so ANCOVA is basically a combination of factors and continuous variables. Okay, again losing my voice. Let's see. So we have. These are the observations, Nij, right? So Nij is just the observed jth value in each sample. So now we split samples. We have I samples, which is equal to the number of levels in the factor. So in our case, 5 cities, for instance, there will be just 5 samples. And then the observation has a double index. The first index gives which sample it is, which level it belongs to, and J is the jth observation in that sample. Okay, and then samples do not have to be of the same size, so they have sizes n1 and so on, nl. If they are, that's the most most common case, that you take just the same amount of observations for each level, and that is called balanced design. Okay, so then we assume that that expectation of Ij is eta I. That means what? That means that in each level, each observation has the same mean. Okay, so they could be different per sample, per level, but within level they're all the same. Okay, so we are using here E as an expectation. I hope it's all known, and I will maybe touch upon this. There is the variance of the random variable. There's a covariance of 2 random variables. These are operations which we will encounter here in this course. Okay, so this is how we can write down this ANOVA model. So this is just the observed value, and it's represented as its expectation of that random variable plus so-called random error. So you just basically what you have here is just the difference between random variable itself and its expectations. So there is always some random variable which is equal to the difference of the observation, and it's to the random variable minus its expectation. Okay, you could think of that random variable as an error. Okay, so you observe something deterministic, which is expectation, plus something which you could think of as an error. And then, of course, by definition, the expectation of that error is 0. And now we come to the assumptions. We assume that all these errors have the same variance, sigma squared, and they're uncorrelated. For now, we are not assuming anything, okay, anything else, just uncorrelatedness, and that they have the same variance. That's it. So for now, it's good enough. The next thing, we reparameterize this eta I, okay? Please go through my recorded lecture where I try to explain all that. The idea is that of reparameterization is that we will be needing this in two-way ANOVA. It's not needed in one-way ANOVA, but we are still doing it simply for the sake of explaining why we are going to do this in a two-way ANOVA. In one-way ANOVA, this is kind of overkill, okay? You don't really need to reparameterize. So you can do everything without reparameterization. But we're still going to do this as a preparation for this step, which will be necessary in two-way ANOVA. Okay, there it will be crucial. It will be crucial to reparameterize. Okay, and here we just do it somewhat artificially. Okay, so but that's just, you know, for the sake of the future considerations. Okay, so instead of eta, we just write mu plus alpha I. Okay, so there used to be just one eta I unknown. Okay, there were E unknowns, and now there will be E plus one unknowns. So we actually made our life more difficult. We actually introduced an extra unknown. So there were eta 1 and so on, eta I. So I unknowns, I big unknowns, but now we'll have I big alpha unknowns and plus mu unknown, so it's I plus one unknown. So we made our life more difficult. Okay, just simply substitute this in there. So this is how the model looks like. And think of mu as something which is common for all levels, and alpha is kind of a responsible part which is responsible for level itself. So if levels are different, then they're different, and alphas are different, and mu is the same thing. And mu just stays there. It's always fixed for it's always the same for all five of them. Well, in this case, it's general, it's I. Okay, and now what we're gonna do, we're gonna put all the samples. So there are I samples, that's the first sample, okay? This is the second sample, okay? And this is the last sample. We put them on top of each other. We make very lengthy vector of observations. And we do the same with errors, okay? And we do the same with parameter, okay? So we make from parameters the vector, from observations very lengthy vector, and from error is also very lengthy vector. And they're all columns. You see that's transpose, transpose, transpose. So you could think of them as a columns. And now we write our model just in the matrix form. So we don't want to write these many equations. So you remember there were many equations here. See, so n equations. Instead, we just write one equation in the matrix form. We now say that our observation y is equal to some matrix x times this beta plus error. We just need to figure out what is this matrix x to have what we had, right? We want this back, right? We want this back. So therefore, we want to understand what is this matrix x to have those many equations before. So this matrix is called incidence matrix or design matrix. I prefer the term design matrix. I think it's more used. And then we assume that the expectation of this vector is 0. The expectation of the vector is vector of expectation by definition. And the covariance of the vector, it's a matrix. It's just a matrix consisting of the pairwise covariances. And this matrix is consists of everywhere 0 except sigmas on the diagonal. And sigma on the diagonal, it's exactly variances, okay? Variances of the individual coordinates of our error vector. Okay, let's see how matrix looks like. This is how it is. This is how it looks like, this matrix. let's just see, okay, just one very quickly. So y11 has to be equal to mu plus alpha 1, right? So then this value has to be equal to mu plus alpha 1 plus E11. Okay, let's see. Y11, and then we take the first row, multiply with this one, and we have to get mu plus alpha 1. That's why we have 1, 1 here, and the other two zeros. Okay, that should be clear. And that goes for all observations of the first sample, of the first level. So it's going to be always mu plus alpha 1. So therefore we have the same thing here, and then 0, 0. And then of course it changes, then it becomes mu plus alpha 2, and then 1 is here. And this is responsible for alpha 2, all the others are zeros, and so on. And then the last one is here. Okay, this is how this matrix should look like. So it's simply constructed by the definition of the model, and it always going to be a matrix which consists of 0 and 1s, and it always going to be matrix which has a vector of only 1s and as the first column, and all the others are going to be like this. Okay, so it's just 1s, and then the rest is zeros, and then zeros, and here 1s, and then zeros. Okay, so it should be clear. And then what we're going to do, we're going to simply apply the least squares method. We simply make such a function. Okay, I will, let me just concentrate on this expression because this expression is at least for me most clear one. So we just look at the distance between vector y and x beta, which is on the right hand side of the model. So we compute a squared difference, a squared distance between these two, between these vectors, this vector and this vector. This is what we are doing. And we'd like to minimize that distance with respect to the beta. Beta is the parameter. So it becomes a function of beta, and it's a very nice function. It's a quadratic function. It's perfectly differentiable, and it's perfectly minimizable. And so the solution is this. Okay, so the beta which would minimize this function should satisfy this equation. Okay, and the question is there unique beta, or there are many betas? Well, it depends. It depends on whether this matrix, which is here, when we take a derivative of this and set it to 0, we'll get that this boils down to this. So beta hat, the one which minimizes this one, has to satisfy this. Okay, and now the question, can we find unique beta? Well, only if x transpose times x is invertible. Okay, only then you can find it. Then, of course, we just simply multiply with x transpose times x. This is the square matrix, by the way. And then if it's invertible, we multiply it so it disappears here, and then we'll get a nice expression. You see this one, and then that would be the unique solution. But it's only possible if this matrix is invertible, which is the same, which is equivalent if x, the matrix x, is a full rank. A full rank means that the columns of this matrix are linearly independent, all of them. And now let's go back to our example. Is that the case? You see, this is our columns, this, and this. Are they linear independent? Well, no, because just take second, third, and fourth, sum them all up, make a sum of this one, plus this one, plus this one. You will get the first column. So the first column is the sum of the others. So they are not linear independent because the first one is there, which sort of spoils. All the others are actually linear independent, and they are even orthogonal, you see, because the second is orthogonal to the third, and also the second, third, and fourth, they are orthogonal. But The first one is sum of these three. So it's not possible, simply. So we cannot find this. And that's, you know why? That was because we, at the very beginning, we introduced this mu. And once we introduced this extra parameter mu, we actually created this column and we actually spoiled the whole thing. We actually made this matrix not a full rank, and we actually spoiled our conclusion here. We cannot simply have that. So we have to go back and we have to do something about it. Okay, for now we sort of, you would say, why did you do this in the first place? Well, I said why, because it's for the sake of the future considerations. Okay, we'll have to sort it out now because we will have to sort it now later on as well. Okay, let's do it now then. So we simply do the following. Since they're linearly dependent, we only need one linear restriction to make the solution unique. Okay, now the solution is not unique. Okay, you can write down this formula. So there is still a solution here. You can find the solution, but there will be many solutions. And to make this solution unique, you need to introduce one linear restriction. And then it could be a different linear restriction. The first one is just set mu equal to 0. Basically, that's means that we remove the first column, and then everything is fine. That's exactly where we started with. So remember, and if we remove this column, then we can resolve. Then there are only alphas. And then each alpha is just a level average. Okay, so we take average over level, and that's it. It's very simple then. Another way of resolving it, and that's what we're going to do in the two-way ANOVA as well. This is why we're introducing this mu. Okay, you would say, why did you introduce this mu in the first place? Okay, but imagine, so here I just get rid of this mu as if it's not there. But now I want to keep that mu. So then I need to introduce some other condition, some other restriction. And this is the restriction then. I say, okay, I keep mu, and instead of setting it to 0, I just say, well, I just require that all alphas are equal, sum of all alphas is equal to 0. Why not? It's and then that's actually boils down to the solution that we have now mu hat and alpha hats, and the solutions are found. So now mu hat turns out to be the overall mean, and alpha hat turns out to be the level mean minus overall mean. Okay, and if you just sum them all up, you will get that sum of alpha hats, the solutions, is equal to 0. So it does require, of course, our restriction. Well, it has to, because we require that. We impose this restriction, and solution has to obey. All right, and then let's see. Oh yeah, we'll have 5 more minutes to go before the break. Okay, so let's just stick to the first constraint, mu is equal to 0. This is just let it be our restriction, which is basically as if we started with the very first model, right? Remember with etas. Yeah. So mu was not there, and setting mu to 0, we are basically throwing that again away. And now we need additional assumption and normality. So we used to have errors to be just uncorrelated, and that's it, and having the same variance, but now we require that they're normal, and they're normal, and since they're uncorrelated, then also independent. They're independent. We assume that they're independent, normal, and then of course expectation 0 and variance is sigma squared as it was. Now, since so mu is equal to 0, we know that there exists a solution of this vector beta, which exists of mu equal to 0 and alpha hats, which we found. And then we just substitute this solution here. Okay, we found this as a function of data. So now we get something which can be computed, okay, only based on data, and it's called residual sum of squares. It also has a name within group sum of squares. What does it say? It says the best fit we can get, okay? So we actually minimize this sum. So then beta hat is the minimizer. That's the best we can have. So that's the best fit over our big model, okay? So when we allow all betas for I, and that gives us what we can actually obtain. That's as the best fit, and this is the error of that fit. Okay. Okay. Now something very important. Here is background information. Okay. Actually, all of it. So there people write a lot of books on ANOVA with like things like this, double sums, triple sums, and more, and book dedicated only to ANOVA with deriving all this, what I'm going to say now, and just. But actually, this whole thing can be very easily derived. But for that, you really need to make a step up a little bit in your abstraction level. You really need to operate in terms of projections of the normal vectors. Okay, I'm not going to that because I know people who are sort of not happy with this, but the background information is here. And if you do that, then everything becomes very clear and everything sort of can be derived in a very elegant mathematical way. It's a whole bunch of this, making a huge amount of books actually obsolete, which are written on ANOVA. And all these double sums, this is really crazy. There is no need for that. You can look at this from the point of view of projections. It's just the squared norms of project certain vectors in certain spaces. If you look at this from that point of view, from very mathematical, again, you need to go to that level of abstraction a little bit, and then everything becomes really okay. This is the point. Okay, we can prove, and it's actually proved in the lecture notes. But also not really elegantly, it's just directly proved. So that thing S omega turns out to be, if you divide it by sigma squared, turns out to have chi-square distribution with n minus rank of x. The matrix X has a rank, okay? This the number of independent, linearly independent columns. With this many degrees of freedom. Okay, let me remind you what is chi-square distribution. Chi-square distribution is this. Just take Z1 and so on, Zk, identically distributed, normal, 0, 1, okay? And then take sum of squares of those. So then you have a new random variable y, and that random variable has some distribution, and that distribution is called chi-squared with k degrees of freedom. That's it. This is how this distribution was introduced. That's exactly the distribution of that resulting random variable. And now the claim is that this S omega divided by sigma has this distribution, okay? Rank of X, what is the rank of X? This is the number of independent, linearly independent columns. Okay, let's go to our example. So how many linearly independent columns here? So we have I is equal to 3. So we know that if we this plus this plus this, so we get this this column. So at least one column is linearly independent. Throw that away, and then you see that all the other form the basis, orthogonal even. So the biggest number of linearly independent columns in this matrix, and it's always the case. It doesn't matter whether it's E is equal to 3 or 4. It's going to be like that all the time. So there's exactly E and the linearly independent columns, and therefore this rank here is equal to E, and therefore the number of degrees of freedom of this chi-square distribution is n minus e, okay? Since it's chi-square distributed, random variable, we can take expectation of that. That's the same as taking expectation of sum of z's squared, where k is equal to n minus I. Expected value of a standard normal random variable squared is equal to its variance, right? So it's 1. So if we take expectation of that thing, it has to be equal to the number of degrees of freedom. That's exactly written here. So expected value of this has to be equal to n minus I. Now try to compute that directly. It's going to be such a difficult job. But just reasoning that this is chi-squared, so it has to have the same distribution as this one, you can easily compute that, okay? So you can easily see that it must be n minus I. There is no other way because it has this distribution. And then, of course, what you could do, you could just put n minus I to the to the denominator here and sigma squared there. So basically, this is true then. And that means that this is an unbiased estimator of the variance, okay? And now, just coming back to this t distribution, remember, in the t distribution, we had two levels. So that thing is also there. So, and then n minus 2, remember it was n minus 2. You had to divide by n minus 2. Why? Well, that's why, because the number of categories of levels was 2. And that's why it was the only then that thing was unbiased estimator. And then there is, of course, explanation here, mathematical explanation here. I think we should have a break. Let me stop sharing, and and I propose that we have a break and put the and I will go through the chat in the meanwhile, and I'll try to react to some of you. Yes, okay. We have a break for 15 minutes until 14:31. Okay. Okay, let us resume our session. So my plan is to finish up this theory part, and then we'll go to our demonstration. Couple of questions were asked. I answered some of them. Okay, concerning the people from previous year, yes, you can keep your grades from the last year, from the previous year. The problem with the grades is the following, that we cannot put them in the grade center right now because assignments are not open. So somehow I can just grade center doesn't allow to put grades before assignment is open. So what we can do, we can put them some sort of note there. I created a column called note, and then we just say, well, grades from the last year, and of course I will have to check last year grades, but please, those who are taking part in this year from last year, please send me or one of the TAs email saying that you would want your grades to be counted for this year for the assignment. We allow that, and then we simply put them in due time, not right now. We cannot do that because grade center doesn't allow that. Okay. Let's see. So let me start sharing screen again. So other questions could be asked also in the chat, and so this is this very important property, which is highly non-trivial, I would say, and requires very somewhat elaborate proof. All right. Okay, now let's go to the null hypothesis. Okay, what does null hypothesis say? This is what we want to test. We want to test whether all alphas are equal to the same value. Remember, we set mu to be 0, so we just stick to this parameterization when mu is equal to 0. And then zero hypothesis says they're all the same. If they're all the same, then our model becomes very simple. This is just all observations are equal to alpha plus noise. So therefore, I write it again in matrix form. But now this is exactly our matrix. This matrix consists of only one vector, which is just 1, 1, 1, 1, 1. Well, all the other things remain the same, but what changes this matrix X, which now consists of only one vector, and which boils down to a very simple model. And this model is called omega small, and it's a reduced model. Of course, this is the submodel of our big model when we have matrix X here, remember? So this is when we let alphas vary, of course, we have a bigger set of possible models. This is, and of course, this contains this particular case. So therefore, our reduced model is submodel of this big model. And basically, what we want to test, now think of terms of models, we want to test whether this reduced model as good as the big model. Okay, this is what we want to test. So this is a reformulation of testing in ANOVA. So reduced model implies that the mean response is the same, and if all alphas are if all alphas are the same, this means that factor has no influence. So there is no factor. So words, there is no factor is not present, can be formalized mathematically by saying all alphas are the same. Okay, we do the same thing, what we did for big model. Now it's a small model, so we compute alpha hat. There is only one alpha to estimate, and it is done very easily. It's just overall mean, of course. There is nothing else which can do better in this optimization problem. And then the corresponding S omega is called total sum of squares. Okay, that's the best we can do in reduced model. Remember, reduced model is a smaller model, gives less possibilities. That means our fit is going to be worse. We are not going to do better than for big model. For big model, we had many parameters to tune. So we had a lot of freedom to make a model to have a very good fit. But here, our fit is going to be worse. Okay, remember that. So what is the rank of our matrix now? Okay, well, this is a simple matrix, just vector of ones. Rank is 1. So now we get the same story. So this S omega divided by sigma, again chi-squared, all the same, nothing changes. This principle is just very uniform. As long as you do this over some model, you always get n minus rank of that matrix, the one which is involved here. Okay. In this case, it's 1, so we have chi-squared n minus 1. Okay, the same story, S omega divided by n minus 1 is also unbiased estimator of sigma. Okay. In fact, many of such unbiased estimators you can find, as long as you put some matrix here and then you just compute its rank, and then you compute its sum of squares. This principle goes through for any choice of a matrix X. And now what do? Now we do the following thing. Remember, this is our bad fit. This is the fit over reduced model. Okay, the one which specifies the null hypothesis. So null hypothesis means we can all alphas are the same, so our fit is bad. We cannot. There is not much flexibility. Here is the big model. Our fit is good. This is the error in the good fit. This is error in a reduced model fit. And you just compute this difference. Well, although it doesn't matter to us how it looks like, but you see it's some positive value, of course. So this is always bigger than this. Okay. One more thing is this. This is random variables. This is random variable. This is random variable. Remember, they're both chi-squared. And then we take a difference between them, and it turns out to be independent of this. I explain here mathematics behind of that, because they're projecting on some orthogonal spaces. But those who are worried about this, just disregard this. But the fact is that this random variable is independent of that. And again, this thing works. That's S omega minus S omega divided by sigma, again chi-squared. So where does this I minus 1 come from? Okay, remember that one is with n minus 1 degrees minus this one, n minus I number of degrees. So that minus that gives us I minus 1. Okay, this I minus 1 appears from the difference of degrees of freedom of that thing and of that thing. So basically this random variable is sort of a an ingredient of that one. So by subtracting S omega big from here, we're actually decreasing number of degrees of this one. So it used to be n minus 1. And then that one is sort of a subset of that. So we just decrease some of those degrees, and it boils down to E minus 1, I minus 1. Okay, so now what? Now, in principle, that already gives us a lot, right? So you see, in principle, we could have used this as a statistics for testing. So is null hypothesis is there or not? Is there factor there? Okay. Oh, sorry, factor there means null hypothesis rejected. So this is no factor, and this is factor. Okay, this is the reduced model, and this is the full model. So if difference between them is big, that means reduced model is as good as the big one. That means there is no factor. So basically, you don't need big model. You just take small model. That small model is good enough. That means no factor. Factor doesn't play a role. So we would do this testing just by looking at the quantiles of this chi-squared. Yes, everything would be fine, but there is a big problem. This sigma squared is not known. So we cannot use that as a, we would have used that if we knew sigma squared, but we don't know sigma squared. And now we're going to do something which is kind of very artificial, which Fisher did. And actually, that's the only thing you could do if you don't want to use sigma squared. You want to substitute sigma squared with something, okay? You substitute that with the estimator, basically. And that's all you can do. And once you do that, then, of course, this distribution changes. Remember, it used to be normal, and then you divide by S, the sample standard deviation, and then it goes to T distribution. The same happens here. We would have used that if we knew sigma squared, but we don't know the sigma squared. Therefore, we have to substitute sigma squared. Still, it's a good thing. The difference is the right thing to use as a statistics, but sigma squared is unknown. Okay, what do? We divide by the estimator of sigma squared. And we divide by something which is independent of that. Okay, and you see what we get. So this, let me introduce first what is the F distribution. So F distribution is the following thing. Suppose we have V, which is chi-squared with m degrees of freedom, and W, which is chi-squared with n degrees of freedom, and they're independent. Now take the following. Take the first random variable, divide by m, and then divide. Second random variable, divide by n. So these two are simply normalized chi-squareds, and they're independent. And then the resulting random variable is called, which is, I denote here y, has some distribution, and that distribution is called F distribution. It was introduced by F. And that was the only reason to introduce this distribution, just because this is distribution of one normalized chi-squared divided by another normalized chi-squared. And it's called F distribution with m and n degrees of freedom. Remember that the order is important here because we divide this by this. If you exchange these things, then you will get a distribution of 1 over F distribution, okay? Okay, so now what do? So we need to put sigma here squared, right? But sigma squared is unknown. Therefore, we imagine we put here sigma squared, and we put here also sigma squared. Then it sort of cancels. But then we can say that this is chi-squared divided by another chi-squared. So that would be chi-squared. This chi-squared divided by sigma, and we divide by its degrees of freedom. That's exactly what we are doing here. And in the denominator, it's another chi-squared. And we put sigma here as well. And we also divide by the number of degrees of freedom. So basically, we are in this situation, and that means this is an F distribution. And why we don't have sigma squared? Because it's canceled, because it's a ratio. So this is chi-squared divided by chi-squared, but sigma has disappeared because it's a ratio. So therefore, we don't have to use sigma. Normally, we have to use sigma here, but if we make a ratio of the two things, then sigmas here and sigmas here, they cancel each other, and then we have chi-squared divided by chi-squared, and that's the only reason this whole, construction, this construction is only for the sake of getting rid of sigma, and then we end up with F distribution with what parameters? Well, the number of degrees of freedom, I minus 1, n minus I. That's it. And then from now on, we just do the testing. So if this is big, that means as omega small is far away from as omega big. That means bad fit reduced model is doing bad. That means factor is there. So it's important to consider factor. But if it's small, if it's not too small, if it's not too big, then we say, well, reduced model doing as good as the big model. That means factor is not really important, okay? Or You can another interpretation is that so the variation in response between groups, that's the one, is much larger than the variation in the response within groups. So you see, between groups becomes important. That means that the factor is actually playing a role. Or I prefer this one. Omega fit is just bad. If this statistics is big, that means omega small fit is bad. That means zero hypothesis is not appropriate. Okay, so this is how you do the testing. Simply compute the value of that statistics and then compare to the quantile, or just compute the p-value. Okay, this is just the random variable which has this F distribution. This is the exact value of that statistic which you can compute now. Okay, and then compare to alpha. Okay, this is already a simple part. I think the difficulty here is construction of that test statistics. Once you've done that, you know its distribution. It goes like a charm, and it goes in the same way as a t distribution or any other distribution. You just compare to the quantile or the compute p-value. Okay, if you do that in ANOVA, so you will get as an output of R, and this is really important for you to know for exam, because one of the questions, it's classical thing, it's based on ANOVA table in its interpretation. Well, you will see that also in the practice exam, and you will see that in the exam from the last year. So basically what you will get then as an exam question is just this ANOVA table, but filled only partly, and then you'll have to fill the rest of the table and then do testing, in fact, by using that table. And this is what you get to see. Okay, the real output is like this. Okay, so you will see these things. What they mean this. Okay, it's just I just put the explanation of what those numbers here mean. So here this number is just I minus 1. This is the number of cells minus 1. Here is within groups the degrees of freedom. It's n minus. It's a degree of freedom of this random variable. So this is S omega between groups. This is the between groups sum of squares. And it has this many degrees of freedom. Now you take this, divide by this, and that's exactly what you put here. Now you take sum of squares of the within groups, the sum of squares, divide by this, you put it here, and now you take this term and divide by that, and that's exactly your F statistics. And then you compute this probability, and that's p-value. But for you, if as a user, when you get this table to see, you immediately look at this. That's the most important. So you just see the p-value, small or big, and that's it. This is what you. This is, of course, it could be interesting and for practice purposes, but most of the time you're interested only in this p-value, okay, whether you reject H0 or not. Okay, and then you do model diagnostics. Actually, ANOVA model is based on assumptions. Okay, remember there was normality, they're independent. So you really need to make sure at least they're not violated too hard. Okay, so you cannot really guarantee, never guarantee that these assumptions hold, never. But at least you can make certain checks. And then these are the checks you're supposed to make. Okay, this is the in your assignments, and there are many more, but we just stick to these 4. So you just plot fitted values y hat. What is y hat? Y hat is this value. Okay, I should probably put here equal to. It's given to you by R commando. We'll see that. So this is basically your prediction. Okay, you of course have observations, but you can also have a prediction. When you compute beta hat, then you can compute x beta hat, and that's exactly prediction, and then they're called also fitted value, and you could put them against the residuals and then scatter plot, and then you could also do QQ plot of the residuals. Residuals are supposed to be estimators. They're estimate error vector, and under model assumption they have to be normal, right? This is our assumption. So we can estimate them and look at them, and they should not deviate from what normal distributed random variables would show. This is very important. There is Bartlett test for constancy of error variance. Okay, that's just one of them. And Shapiro-Wilk, which I don't really like very much because it's very unreliable, but it's better than nothing. So it gives you a test for normality. So whether you reject normality or not. So it will give you a p-value. And if p-value is very small, then you reject normality. Okay, and then if there's assumptions fail, well, you have to do something, but let me not go into that. Okay, there is one more thing which you could do when all normal, say you check and it's certainly not normal, and then you say, well, I cannot do ANOVA because there is normality, the assumptions do not hold. What you could do Kruskal-Wallis non-parametric test, which does kind of the same, not exactly, of course, but it does sort of the same as ANOVA, but it doesn't rely on normality. So what he does is this. It's called Mann-Whitney for 2 samples, and Kruskal-ANOVA if there are more. I don't know why there's 2 different names. So you have I samples again, and then you actually test the null hypothesis that they all come from the same distribution. And your test is based on ranks. And ranks is a very stable quantities. So you don't rely on normality. Ranks is something which is very stable. Of course, this test has less power. I'm not talking about power at all here, but in principle, it's not as powerful as ANOVA under normality, but it doesn't rely on normality. It has its merits. Against alternative that at least 2 of the distributions are not, and you just apply this test and see whether it gives you the same as ANOVA, just to sort of back up your ANOVA. And maybe sometimes if you don't you see that assumptions are not satisfied, then at least you could provide Kruskal-Wallis non-parametric test. Okay, let's just go to example. Let's quickly, and then I will go to our by the way, when we're supposed to end, I'm not sure when. So coffee sales examples for 5 cities. Are the averages the same? Well, we have 5 samples, 5 levels, 10 per each. These are the box plots. I will run now after this R, and we'll see how it works in R. We can get the estimator for beta, and here it depends. Remember, we stick to the parameterization mu is equal to 0, and you really have to specify which parameterization you use in R. I will show you how to do that. At this moment, we are dealing with the parameterization mu is equal to 0, therefore there is no mu. And then we will get only alphas, and then we will get this estimators in that parameterization. But you have to be careful which parameterization you use. For testing, it doesn't matter which parameterization you use. It will be the same test, it will be the same p-value, everything is the same. But for estimating this beta hat, it does. So beta hat is something else. It's just for you to see what the estimator is. It is not used in test. In test is just this test statistics, whatever that comes out. Any parameterization leads to the same test statistics. So ANOVA table is going to be this, and then you see these numbers. And then you immediately look at this number, okay? That's the most important number. So p-value is very, very small, okay? So it's, well, 10 to the power minus 10th times something, and then it's really small. So what is this S omega big? S omega big is this number, remember? This difference S omega small minus S omega big is that number. Now this number divided by that number should be this one. This number, this is S omega big divided by this number is equal to this. Now we take this, divide by this. This is F statistics. That's the value of F statistics. And then we compute p-value of this F statistics with this degrees of freedom. So it's I minus 1, 5 minus 1 is 4, n minus I, this is 50 minus 5, 45. And then we compute this probability that this random variable is bigger than this value, and that's exactly very small. And then, of course, we can find sigma squared, the estimator for sigma squared. This is just S omega divided by this, and that's the number. Okay, we can take a square root of that. And then a very small p-value implies that evidence against H0 is strong. We conclude that mean coffee sales are not the same. And the Kruskal-Wallis test, if we run, we get also small p-value. At least it shows the same result. That's the same, it leads to the same conclusion. That's good. Okay, diagnostic checks. Okay, I already mentioned them, residuals, and then fitted again residuals, QQ plot, Bartlett test. Bartlett test is this, 0.8. And that means we do not reject the hypothesis that sigma is the same. And then Shapiro-Wilk test gives this value, p-value is not big, not small, sorry. So therefore we do not reject normality. And these are the plots. So this is the fitted value against residuals. So residuals must be kind of normal. So they must be they must be symmetric because normal distribution is symmetric. From minus something to something because we don't know sigma. So it looks okay. So there is no pattern here. You should see whether there is a pattern here. Then it's not really a good model. And QQ plot is kind of okay. Okay, let me stop sharing and go to just whether you have some questions or not. Where does 50 minus 5 denominator come from? Okay, that's n minus I. So the number of distribution is n, and the number of levels is I, it's 5. So that was exactly in the theory that we divide by n minus I, our S omega big, we divide by n minus I, and that was exactly the value. So 50 is n and 5 is I big, and that's why we this number appears there. Okay, let me share. Let me run R. So it should be, I should be able to share now. Okay. Okay, I hope you see R. Oh, by the way, this is the template for the assignments, possible template. It's just this RMD, and then you say CNEAT here. You see this CNEAT, and then it will produce you PDF file. Let me maybe show you at the end, but let's go to this script file. Okay, here it is. So this is the coffee data. Let's just run it already. And let's have a look at this. This is just 2 cities for now. Oh no, it's already 5. You see there's just 5 cities, and these are the sales. So there are 5 columns. And you can do t-test. Let me not do t-test, okay? That's kind of simple. You just go through this by yourself. Let's just go immediately to the one-way ANOVA. Okay, what we need to do, we need to say, we need to put them all these columns on top of each other, create some very lengthy vector. So we do this sales, and we put them on top of each other. Let's have a look at what we get. Okay, so it's a very lengthy vector. So the first 10 is from what is it, from Amsterdam, the next 10 from Den Haag, and so on. Okay. Now we need to specify the factor, the city. So now the next vector will have to say from which city this comes. So the first 10 should come from Amsterdam, right? So let's just introduce this vector city, okay? And then we say its factor, and it has these names. We assign also names just for, you know, to have it nice. So let's have a, yeah, you see the first 10 Amsterdam, the next 10 Den Haag, and so on. So this vector should correspond to that vector, the previous one, right? Actually, you don't need to put them on top of each other. You can shuffle around, but it's fine as long as your factor vector corresponds to that. So the first observation comes from Amsterdam. It has to be Amsterdam in the corresponding vector of factors. So we created the first sales and city. Now we put them together in one matrix, in one together as a data. So let's have a look what we created. So this is what we created. We created just two lengthy vectors. You see sales and city. So here's sales and from each city. You need to create this from your original data. A little bit of work, not so. Okay, then we can have a box plot, for instance, if you want. Well, all 5 of them. And then this is the crucial, what you need to do. You create the so-called model, okay? This is how ANOVA runs. You create model. You say LM, linear model, and the sales is response, a city is factor. And then you say which data you apply it to. The data should contain these 2 columns, the first column sales and the second column city. And sales is just numerical vector and city is factor. You have to make it factor vector, okay? So it could be numerical. You need to insist that beforehand so that you know for sure that ANOVA will be applied. Okay, then you create this model, okay? And now you say ANOVA of the model. So a whole bunch of things is now in the model. So you can do a lot with that. Among other things, ANOVA, you can sort of ask, extract me ANOVA things from model. We are now asking what, so extract me ANOVA things. Okay, that's it. You get this ANOVA table. That's exactly I minus 1. This is n minus I, okay? This is this S omega small minus S omega big. But you don't care, you just look at this p-value, you see, oh, it's small, okay, reject H0, that means city matters. It's important which city. So as long as you see small p-value, okay, if very simplistically, you just put what I did, you just do what I did and then run this and then look at this p-value and you're done with the analysis, basically. I mean, at this stage, of course, if you're not, okay, but we're interested in estimates, right? And then you say summary, but you see this is new, and this is not really, this is a bit of a problem. You see there's only 4, there are only 4 of the cities, because what R does, it does it in a different parameterization. The one I even didn't discuss. So that is called treatment parameterization, and treatment parameterization gives you differences with the basis, or it chooses the basis city, which is in this case Amsterdam, and makes differences. So to go to the right one, you have to say sort of do this, go to the right parameterization, the one we actually interested in, the mu is equal to 0. Then you do this. I will come back to this treatment parameterization in two-way ANOVA. For now, we just do this operation, and that's exactly, that will be alpha 1, alpha 2, and so on. Okay, here's explanation. If you want estimates for mu and alpha 1 and so on, the one which is the ones which are for the second parameterization, sum of alphas is equal to 0. Oh no, that's exactly the one we are interested. Okay, let's just do this. We need to say contrast. It's given by the contrast command. So contrast command, and then we again create a model, which and then we say summary, and this, and now we are for our. So this is mu. Estimate of alpha 5 is not shown. Okay, and now we get mu, alpha 1, alpha 2, alpha 3, alpha 4 in the parameterization when sum of alphas is equal to 0. Okay, this is another parameterization. And why is alpha 5 is not shown? Because I don't know why, but our developers, they decided not to show it because they say, well, you know that the sum of them is equal to 0, so you find yourself alpha 5. So alpha 5 is actually found from this, that sum of all 5 is equal to 0. So basically you need to sum this 4 and take a minus of that value, and that will be your alpha 5. Or you change the order and then you will get alpha 5, one of these 4. Okay. Checking the model assumptions, for instance, QQ, we've created model, and then you say residuals of model, you just get residuals of model. Okay, you can see them. So these are the numbers. And then you say QQ norm of that, and then you will get that. That's exactly what I got. Shapiro test of residuals, okay, whether they are normal or not. That's very simple, just this p-value is this. It's not small, so normality is not rejected. Now plot fitted against residuals. We have models, so everything is in the model, and we just extract from there what we need. So we need fitted, we say fitted of model. We need residuals, we say residuals of model. And then we can play with the plot, of course. Okay, let's just run me this. Okay, this is exactly the picture, and you can say you can put some titles here if you want, and then add a line as just you know, I don't know, just to show that there is a 0. Oh, low battery, Jesus. Let me. Sorry, it was low battery. What I see here? Okay. I'm still on the line, I think. Okay. Okay. This is not there. So this is online, right? This, okay. There it is. And now the last thing is Bartlett test. And this is also pretty good. So Kruskal test, let's run Kruskal test over sales and then over CT. You have to keep this vector and then sales vector, the response vector. And then this is this very small value of the p-value for it. And two-way ANOVA we'll do next time. Okay, I'll stop share and I'll take questions now. I hope this was clear. So you go through this R script and try to understand all the commandos which are there. I have as comments there some explanations, and please keep. So look at the Canvas page, because I will make a pre-recorded lecture of the next one. Hopefully somewhere in the weekend. and I will place that in due time on Canvas, and that's going to be our style. Although today I was sort of more like a lecture, less than like this going into, like, it was not much of a complement to the of what I did, but more like a repetition of that. But I will try to move towards the setting when pre-recorded is like a theory, and then a complement of that in a live session where we discuss things and do some simulation, and I explain some certain points in the theory, which is in the pre-recorded part. Okay, please go ahead and ask me questions and remarks. I'll take some time to sort of let you think a little bit, and maybe formulate a question. What you next? Would it be possible for next time to record the parts of the lecture where you're explaining R code? Yes, I in principle can. But in principle, R code, all that is actually a practical part. So you will get that again in the practical session. So I'm sort of taking over of the work of TAs in a way, a little bit. Because, so there was, by the way, a question about practical sessions. So we will have 3 live sessions dedicated to like theory. And then there will be session, only practical one, hosted by TAs, where it will be totally dedicated to R and also theory, a little bit of theory in assignment. So assignments consist of 2 parts, theoretical and practical. Practical has to do with R, and theoretical is more like mathematical manipulations with certain, well, related to the theory of the course, and then they will. So their job is to guide you through those 2, including also our things. So it's going to be there as well. So please prepare your questions, and at that point you are already, started your work on assignment, and you already know quite a lot, but you still have some questions, and then you can get help. You can get an assistance in R and also in the theoretical exercises from TAs. But I will see how to do that, because that would be, repetition. I don't think we need to do like pre-recorded ones, and then there would be just too much repetition there, and then I would repeat it here. That's kind of double for you and for me. I don't know whether it makes sense. Would it be possible for the next time to record? Okay, thanks. Okay. Any more questions? Please go ahead and ask about R, for instance, something. So with respect to R, I hope everybody is known to that. If you're completely unknown, that's a problem, okay? Then you really need to, there is, of course, there are some textbooks on R, and one of them I available on Canvas, okay, in resources R. Pages course, yes. Okay, practical sessions are indeed in the Canvas. Please go check the Canvas page and then go to course schedule, where I scheduled. It's very simple. The first topic will take 3 lectures and then 1 practical session. All the others will take 2 lectures, practical session, 2 lectures, practical session, 2 lectures, practical session. That's very easy. So 3, 1, 2, 1, 2, 1, 2, 1. At the end, I will have a last lecture dedicated to the overview of the course and like question hour for the exam. Okay, that will be just the lecture before exam, and then there will be exam. I don't know, online, I guess. And for online, I will have to think how to make the right setting for the exam, and what kind of exam we should have then online. Yes, so 3, 1, 2, 1, 2, 1, 2, 1. Is it clear to everybody? So you could sort of plan your, and it's all there. So it's all in those spots. And at the same time, like today, it's always on Wednesdays, always from 1 to half past 1 till what is it? 3:15. The roster says written exam. Yes, okay, then it's going to be written, but I don't know. They don't have location. I guess then it's written. Yes, is it? Does it say? Okay, I'll have to check, because to me it wasn't really set yet. Okay, then it's going to be written. Thanks for pointing that out, because I really didn't see that for some reason. If it says written, then they have to give a location, but location is not there. Yes, okay, written exam. Okay, that's true indeed, because you can do an online written exam as well. If it's online, then I'll have to think, really, because I don't think this like it used to be that you're not allowed to use anything. I don't think it will work. So I will have to sort of regard that that the exam is sort of open book exam. So I will have to make an exam in such a way that it becomes kind of open book, more in this style than it used to be. Yes, indeed, because I do. There is, I think, there were already exams, and there were all kinds of things there. So you have some sort of protocol that you have to have your camera like 2 meters away from you, and then you will have to write it down, and you have to sort of scan it, all kinds of things. So I'll have to think how to arrange all that. There is a protocol indeed. Surveillance and all that, online surveillance. Okay, I guess it's good. But the thing is that in the second, also in the second period, lectures are not, they're not marked as online, as far as I saw in the roster. Okay. So there's just lectures, and there doesn't say either it's online or on location. There is no location. The location is not given, but it's also not said that they're online. For the first period, it does say online. It's clear, but well, I'll have to check it again. Let's just not worry for now and see what happens. Maybe educational office. Maybe, but I don't expect they will become all of a sudden live. It's just too much of organization for them, I guess, because you need to take into account all kinds of measures and all that. In other course, by the way, they did arrange one sort of practical session live, but then it has to be the groups. They have to divide in groups because you cannot come together. There would be too many people, and it created so much, of uncertainty, because people are divided in section and then subsection, and only 15 people can attend, and then there must be one TA for like 15, at most 15 people. Well, I don't know. I don't see that happen, at least right now. Well, multiple choice. I mean, yeah, breakout rooms. That's the way to do it, I guess. You mean for exam? We still need to think how to do that with TAs, whether it's going to be just one big session with the two co-hosts, or just break. Well, but I don't think it makes sense. There are only two of them. Well, I don't know. This is a bit of a. It says that the lectures of the first semester will be held online. Okay, then at least I didn't see that in the roster. Okay, so that it's just. But if it's online, then online we just go ahead and do that. Okay. I guess I will have to sort of assume that everything is going to be online. Okay, that's our default setting for now until the end of this semester. So let's just assume that default setting is online, and I will just go on with the setting up the sessions. I will keep the same link simply for the second period, and I should think about practical sessions, how to arrange those. Because if everybody, well, you probably do the same thing. You ask via chat, and they would sort of answer. The faculty, our department provided them. Well, they notified me that they provided them with the tablets where they can write. Actually, I bought it myself, so a Samsung tablet where I can write, but my Mac doesn't cooperate with the Samsung tablet, so that's why I have double identity here. For instance, I can sort of show you how I, for instance, share white screen. That's second me, and then something like this, and then, for instance, the TA would say, well, okay, so variance, so it's a variance of x plus y, for instance, if x and y are independent, okay, that's, so if, then the variance of x is plus variance of y. Something like this, they would do something about for instance, the theoretical questions. Remember, with chi-squared, if, for instance, some variable is chi-squared with parameter k, so that means that this variable has the same distribution as z1 squared plus and so on plus zk squared. So expectation of v is equal to expectation of z1 squared plus and so on plus zk squared, and that's just because it's normal for z1 and so on zk from normal 0, 1. So therefore, so those are all equal to 1. So we have just 1 plus and so on plus 1. So k times k, and that's just k. So that's why. If v is chi-squared distributed with parameter k, then expectation of v is equal to k. Okay, try to compute variance of v. Okay, so this is going to be variance of z1 squared plus and so on plus zk squared. And use this, okay, that the variance of the sum of two independent is equal to sum of variances. Okay, so you have basically sum of variances here. Okay, of z1 squared, it's variance of the squared. And you will need that in the theoretical exercise, for instance. Okay, go ahead and compute it. Okay, it was one of the questions in the exam as well. But it will be assisted, it will be sort of, I hope TAs will give you hints. So something like that they can use. But I think they have this department bought these tablets for them, and they well, hopefully they can use that, something like that. Okay, let me stop sharing here. Okay, is it clear? So breakout rooms work, and I'm out from. Okay. If you need a refresher for RStudio, what you would like to advise to do? Well, there is this. There is some literature. I put the literature on Canvas page. It's a bit overkill. It's a lot there. Let's see. There is also our guide for this course. It's also on the Canvas, by the way. I would advise to read that one, because this is it's very specific for it's just focused on this course. It's focused on our comments for this particular course. So it's written by I think Michael McAfee. He gave that course like 5 years ago, something like this, and he wrote some sort of. Oh no, I think it's Matishka did that, and he changed it a little bit. So I put that online as well. This is available on Canvas under our sources. Okay, so just go there and download that and read it. That would be very, very useful. And I'll go